Good morning, everybody. Welcome back after a nice long weekend. Today we'll really start to talk a little more about the stuff that we use in crystallography. So far we've done introductions, we've done the historical stuff, what was a crystal. Today we'll start talking about symmetry. And as you will realize as the class goes on, you can't escape from symmetry if you do crystallography. Symmetry is very important for crystals, and it's actually our friend. Because imagine if you had to describe an infinite crystal and you had to describe the location of every single atom in that crystal. Who would like to do that? No volunteers? How about a finite crystal? 10 to the 20, 10 to the 30 atoms. Any volunteers here? Still not. Well, you're right. That sounds pretty horrible, right? You would have a job for more than your lifetime, and who would actually care? Nobody would. Luckily for us, there's symmetry. So we've already talked last week about unit cells, the smallest repeat unit. And if that is the smallest repeat unit, that means if we can describe the contents of that unit cell, all we have to do is define the translation vectors, and we can describe the entire crystal, right? We have described every single atom in that crystal. Does that sound a lot better? Sure does, right? Now, there are times when your life could be even easier than that. Because if there's symmetry inside the unit cell, you don't have to describe the contents of the entire unit cell. What you have to describe is what is called the asymmetric unit. Okay? So as long as you can describe the smallest unit that contains everything that is reproduced by the symmetry elements within the unit cell, you've done your job. Now, for certain crystal lattices, that may be the entire unit cell. If you're triclinic, in some cases you have to describe everything in the unit cell. If you're in a high symmetry cubic space group, it can be a very small portion of that unit cell that you have to describe to get the entire unit cell contents. So, let's talk a little bit about symmetry, and let's start with a very basic term, lattice symmetry. Lattice symmetry refers to what your unit cell looks like, okay? How big is it? What is its shape? Now, if that was the only thing that there was, lattice symmetry is a unit cell, we had no rules for how to choose a unit cell, life could get pretty rough, okay? Because you could be choosing any kind of number of unit cells to describe something. Right? For example, on this wall, I could use one of these bricks and choose it as my unit cell, right? Who says I can't use this as my unit cell? Can I reproduce that? I sure can, right? How about I choose this? How about I choose this? I can reproduce all of these, okay? So all of these, by our definition that it is a repeating motif, would be a unit cell. But obviously there has to be some kind of convention, right? Or crystallographers would be all over the place. Now here's an example for what it can look like if everybody gets to pick their own unit cell. All of these unit cells are perfectly good unit cells. All of them will make a repeat pattern, and some of them may look prettier and some of them may look uglier to you. Most of us really don't like something squished like that, but they all make perfectly good repeat patterns. So what are the rules for choosing unit cells? Well, there are two rules that you need to know, and yes, these are rules that you do need to remember. First of all, you choose the smallest possible repeat unit. So this, none of these are good repeat units because they aren't the smallest possible repeat unit. One of these bricks on the wall, that would be a much better repeat unit, okay? Because that is the smallest possible unit. But don't forget about the second part here, and that is with the highest symmetry. That one will actually overrule the first rule to some extent. So we'll see. What this means that we have this second rule is that we can have what we call primitive cells or centered cells. Now I'll give you an example on the next couple of slides so you'll actually know what that means. Now what is interesting here is that it depends on your crystal system. Remember your 7 crystal systems? Not all of them can be centered. Some of them can be centered, some of them cannot be centered. And the fact that some of them can be centered and some of them cannot be centered results in what we call 14 Bravais lattices. Now what's an example of centered unit cells? Here's a nice little repeat pattern. Okay? Obviously if you just look at this without any of these lines drawn on there, there's a repeat pattern for you. Here is the smallest repeat unit, right? We just connect 4 of these dots. And that would be a perfectly good repeat unit. Go in this direction, go in that direction, you will fill all of space. But what are these angles? Or shall I ask, what are they not? They're not 90 degree, right? So, is that high symmetry? How about this one? That one has 90 degree angles, so it's higher symmetry, okay? So we would actually prefer this cell. Is it bigger than the other one? Yeah, it's bigger, right? But it has higher symmetry. Now, this is what we would call a centered cell. The same thing that we find at the corners of the unit cells also appears in the center of the unit cell. Kind of makes sense to call that centered, doesn't it? This is obviously a very simple picture. 2 dimensions, right? We'll see a lot of 2-dimensional examples when we work on concepts in this class because it's just easier to look at. How does it look in 3 dimensions? Here are your 14 Bravais lattices. And that looks like a heck of a lot of lattices, and your first reaction is probably, oh my god, do I need to know them all? Yeah, you probably should know all of them, and you will learn them fairly easily. So first of all, let's look at types of centering. One of the things that you will find here for every single crystal system is a so-called primitive cell. Okay? There is a simple cubic, as they call it, and there's this little letter P here that stands for primitive. Okay? There's a simple tetragonal one. There's a simple orthorhombic one. There's a rhombohedral one for which they didn't even specify the simple, but it is a simple cell, right? There's only dots on the corners of this unit cell. There's a primitive hexagonal one, primitive monoclinic, and primitive triclinic. So all 7 crystal systems have a primitive cell. That one exists everywhere. The centered ones are the ones that don't always exist. Now, there are 3 different types of centering that you need to know about. One of them is body-centered. That's the second one. What that is in addition to these dots on the corners of the unit cell, you have one right in the center of the unit cell, in the middle of the body of the unit cell. That's why we call it body-centered. The symbol for that is I. That's because it was originally named in a different language, German for that matter, and it stands for innenzentriert. That means inside centered if you literally translate it, okay? The nice thing is that also works in the English language. It's inside the unit cell. There's your I. That way you can remember it. After all, we all speak English, so that would be a good language to use. Then we have one that looks a lot more complicated, right? And that one is called face-centered. The abbreviation is F. Once again, the languages luckily work the same. Comes from flächenzentriert. But face has the same starting letter. Where are all of those little dots here? They're in each of the corners of the unit cell, right? And each of the faces of this cube has another dot in the center of the face. That's why we call it face center. Right? And then we are done with cubic. There are only 3 cubic ones. Tetragonal only is listed twice, as primitive and as body-centered. Alright, we'll see a few slides on why that is. Then we have orthorhombic, and orthorhombic is listed 4 times, with a P, with an I, with a C, and with an F. So we've already talked about the P, we've already talked about the I, and we've already talked about the F, so we know what that looks like, whether it is a cube or a brick, right? But what about that C? C is actually base-centered, okay? And if you look at this drawing, what does it look like? Two of the faces have a dot in them, right? The other 4 faces don't. That's what it looks like. Everybody agree? That is what we call base-centered. The base, and of course the corresponding opposite face, have a dot in them. The other ones don't. Now this one is listed as C, okay? And if you look at the unit cells on that little slide, then you will see that these are A and B. So the C face is the face that is between the A and B lattice constants. If we had flipped this thing and it was sitting on a different face, we would call it A or B centered. However, given that we can seat that brick however we would like to, we usually choose our lattice constants so that we work with a C-centered setting. It's one of those conventions, okay? You can give distances in a bunch of different units, but they are conventions about what you usually use. I don't think anybody is going to tell their friend that Pittsburgh is a certain number of inches away, right? Would that be a legitimate unit of measure? Yeah, but it wouldn't be useful. So by convention, we quote things in miles, the same way crystallographers usually work with a C-centered lattice. But if you ever meet an A or a B, this is what it comes from, okay? Somebody just chose the unit cell constants differently, and therefore they didn't arrive at a C-centered lattice, but at an A or B-centered lattice. Now, rhombohedral and hexagonal only have one setting. Same with triclinic. For hexagonal and triclinic, we still use the P for primitive. Rhombohedral is a special beast. It has an R. That's the only time you find that symbol for lattice centering. R for rhombohedral. Monoclinic, once again, we only have 2. Base-centered and primitive. Now one thing we may want to briefly address is, what are these nice dots that are drawn on this slide, right? Because that often confuses people. These are what we call lattice points, okay? So, what is a lattice point? Oh, of course I didn't bring a pen, that's useful. Anybody have a pen? Wonderful, thank you. First of all, let's vote. You think that is really something physical? Or is that a theoretical construct? Theoretical construct? Who thinks it's a theoretical construct? Pretty much most of us think so, and you're absolutely right. It is a theoretical construct. It is something that we use in crystallography because it's convenient. What could a lattice point be? It could be any number of things, okay? The easiest way to imagine this, if you have a problem with these theoretical constructs, is there could be an atom sitting at that corner of the unit cell, okay? If you take a simple metal, that might be how the structure looks. So you have an atom sitting here. In that case, the atom is what constitutes the lattice point. And then you just repeat these things, okay? Either just on the corners, or also in the body center, or also in the face centers. It could be a molecule that is built around that corner of the unit cell, okay? But instead of drawing a molecule, we just put a dot there because that's much easier. So we use that lattice point to represent the entire molecule. Now the thing that really does get a little bit confusing is things don't have to sit at the corner of the unit cell, right? If you have a crystal, is there any rule that says that the molecule has to sit at the corner of the unit cell? Not really, right? We could have a molecule that starts here and that stretches out. No rule against that, right? That would make it more difficult to see how it is translated. Okay, you would have to look a lot more closely. For example, on this last slide, as you can see, it wasn't just a dot. That dot had some shape to it, right? Now this could be something where this arrow extends for a significant amount. Makes it more confusing to see how things are translated. So if I have like a little streak here, a little streak here, 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 then I still need to recognize that there's a translation of 1/2 and 1/2 to get to the face center. You can still see that once you train yourself for it. But it is a lot more easy to see when you simply use a dot. Okay? You could show this to an undergrad. You could probably show this to a high school student. You could probably show it to much younger kids and they could figure out, oh okay, whatever is here at the corner also shows up right in the center of this unit cell. Okay? While younger people might have a much bigger problem envisioning this if you had a molecule that wasn't sitting there. So this is convenient for us to figure out what the translations are in these centered systems. And that's why we draw it this way, because let's face it, all of us still like easy life, right? So you will have to be able to look at something that is drawn and tell me what it is. If I tell you go ahead and draw a face-centered cubic Bravais lattice, I expect you to be able to draw something like this. Okay? So you do need to have some knowledge of these 14 Bravais lattices. Now, we obviously have 4 different types of centering, right? Primitive, body, face, and base-centered. And we have 7 crystal systems. Why do we not end up with 28 Bravais lattices? It's a good question, right? Did somebody just choose to discriminate some of these? You think so? Somebody just discriminated them. Well, you could call it that, but there was a basis for that discrimination. So it was justified discrimination. Here's an example why some lattices cannot have certain centerings. Tetragonal cell, okay? A and B are equal. Let's call them A prime, okay? The C direction is different. So what I drew here is a base-centered tetragonal lattice, just for the fun of it, which, according to that last slide, doesn't exist, right? So I took these little dots in the corners of this unit cell that I drew, and I put a little dot in each of these face centers here. Can everybody see that? So that's a base-centered tetragonal cell, right? But here's what happens. If I just take the closest dots that I can find and I connect them, I end up with an alternative unit cell, right? We already discussed that. You can always do a primitive or a centered cell. Now, given that these two sides are equal, guess what happens to these two sides? They are still equal, right? How about the angles between them? They're still 90 degrees. So this cell here has two equal unit cell axes and all 90-degree angles. What's the lattice symmetry of that cell? A equal B, not equal C, all angles 90. What is that? Yes, you're allowed to cheat and look it up. Just make sure that you know it for the exam. Tetragonal. So, is the new cell higher or lower symmetry than the old cell? Actually, it's a trick question, right? We started with tetragonal. It's equal. So, we have two tetragonal cells, equal symmetry. In that case, which cell is preferred? And I think that is what you were referring to, Indira. The smaller cell is preferred, right? So that one is the preferred cell. Not because it has higher symmetry, but because it has the same symmetry and it is smaller. You can do that with any base-centered tetragonal cell. I made no assumptions about that cell, except that it is tetragonal. Okay? So that is why there is no base-centered tetragonal lattice. It cannot exist. Another cell that didn't list the base-centered lattice was the cubic cell. Any idea why that might be?
Because it'll turn into a tetragonal also at the same time.
The cubic cell will no longer be cubic if it is base-centered, right? It will lose its symmetry if it is base-centered. Because a cube has to have 6 equal faces. So yes, it will no longer be cubic by the time you do base centering. You can have face centering, all faces have something in them, or body centering in the cubic system. You cannot have base centering, because then you destroy your cubic symmetry. So those are the reasons some cells can have all the centering and some of them cannot. For some of the lower symmetry cells, once again, if you did any kind of centering, you could simply find a smaller cell with the same symmetry. The only one that has all centerings is orthorhombic. Okay? The brick. High enough symmetry to have all the centerings, low enough symmetry that you actually can apply all of them. And here's the example that we just looked at with the tetragonal cell, a base-centered orthorhombic cell. There's your brick. Okay, A, B, and C are all different lengths. And I drew it centered, base-centered. If I do the same that I did for that last tetragonal cell, I again get a smaller unit cell, but these angles are no longer 90 degree because the two unit cell axes were not identical. So, by definition, yes, we want the smallest cell, but of highest symmetry. In this case, choosing the slightly bigger cell will give you a higher symmetry. And so you choose that centered cell. Does that make sense to everybody? I see a lot of nods. That's good. So, we've talked about lattice symmetry and about those lattice points. Let's talk a little bit about symmetry elements. Because we said there can be symmetry within the unit cell, right? So far we've still mainly dealt with symmetry that translates. Although if you think about it, that centering already is some kind of a symmetry element, isn't it? So now we'll be talking about all these symmetry elements that can translate atoms or molecules to another atom or molecule within the same unit cell. And there are several different types of symmetry elements. There's point symmetry and there's translational symmetry. Point symmetry will have at least one point that stays unchanged. It could be more than one point, okay? Examples for that are, for example, rotation axes. If this is a rotation axis, any point on this line will not be changed by this rotation axis, will it? Because it's on the axis. It stays right where it is. So at least one point remains unchanged. Here's a mirror plane. Any point in this plane will not move by applying the mirror operation, will it? So once again, there are points that remain unchanged. And then we have something called a rotation inversion axis. We'll talk in more detail about what that is, so don't panic yet if you don't know what it is. You're here to learn that. Once again, there will be a point that is not changed. So let's start with one of the more simple rotation elements, symmetry elements, a rotation axis. Okay? This example shows you a twofold rotation axis. What does a twofold rotation axis do? Well, it rotates by 360 divided by 2 degrees. Okay, so a twofold rotation rotates by 180. Another way to look at it is a twofold rotation needs to be applied 2 times and you're back to where you started. A threefold rotation would need to be applied 3 times until you're back where you started. Given that back where you started is 360 degrees, that means you rotate by 360 divided by 3 each time. So that would be 120 degrees. Okay? So, any n-fold rotation, where n is a number, will rotate the object by 360 divided by n degree. In this case, we rotate by 180. You can draw this with a molecule. You can draw this with a simple picture where a hand rotates. Now, what is important about rotations? One thing is, this is a left hand. What's this? Still a left hand. Just because I rotate around some axis, my left hand is still a left hand. So, a rotation axis does not change the handedness of an object. That is why we also call it a proper symmetry operation. It does not mess with the handedness. That seems almost trivial, right? Okay, fine. A rotation axis doesn't change the handedness. What's the big deal? Well, any of you who want to work with organic or biomolecules might be a very big deal. Okay? How many right-handed amino acids do we have? How many left-handed amino acids do we have? There's a big difference, right? So if you have naturally occurring substances, they'll have handedness. They will be chiral molecules. Most organic chemists try to make chiral molecules. If you have a protein, it can have rotation axes, okay, because they don't change the handedness. Now, our next symmetry element is a mirror plane. Once again, there are some molecules, here are some hands. What does a mirror plane do? If I have my left hand and I look at it in the mirror, it looks like a right hand, right? It looks like a mirror image. That's how we define it, isn't it? So we call this an improper symmetry operation. It changes the handedness. Is it something that is allowed? In many cases, yes. In a protein, probably not, okay? Because in a protein you would need to have all the right and left-handed amino acids if you had a mirror plane. Chances are that's not going to happen. At least the last time I checked my biochem knowledge. So if you have any kind of substance that is enantiomerically pure, be that a protein, be that an organic molecule, you cannot have mirror planes. That's why it is a big deal to know what does and doesn't change handedness. You can sometimes exclude certain elements immediately, just because you know what you're working on. How do we represent it in crystallography? We use the symbol M for mirror. Okay? As a matter of fact, we should probably briefly address how we symbolize our rotation axis. We just use a number. So if you see a 2, that's a 2-fold rotation axis. If you see a 6, that's a 6-fold rotation axis. This is different from group theory, folks, okay? We don't call them C2, C3, C6. Don't use those in crystallography. Leave the C out. We use 2, 3, 4, 6. You can claim that we are lazy. That's okay. But that's our nomenclature. So please use that one. On to the next symmetry element. Inversion centers. It's actually something that everybody knows. At least if you've ever taken a glove and you drew your hand out and all the fingers flipped over. Anybody ever done that? Most of us have done that, right? That is an inversion. Turning an object inside out. Okay? What it is really a point reflection. It's kind of like you take that point, that one finger, and you flip everything over. Everything is pointing the other direction. So it's kind of like you reflect things through that one point. That is what an inversion stands for. What we use is the symbol I for inversion. So it's fairly trivial. Once again, it changes our handedness. And here's actually the proper example of what an inversion looks like. Here's your inversion center. Everything is reflected through that center. If you want to draw that, you would draw a straight line from any point of the object to the inversion center, continue in a straight line the same distance. That is where that point ends up. Okay? The way you can imagine it is as if you have a lens. Everything is focused through one point on a lens, right? That is how an inversion center works. Now, on to the one that you may not have known on that last slide. Rotation inversion centers. Well, they are actually exactly what the name says. It's a rotation followed by an inversion. Okay? So for example here, for a 4-fold rotation inversion axis, you take this hand, you rotate by 90 degrees, that's what a 4-fold does, and then you invert through the inversion center, and you end up with your new object. Now they drew this one here to help you imagine things. This one here is not generated by this inversion, by this one application of a rotation inversion. Okay? This is just an aid in thinking. This one immediately goes to this one through application 1 times of the rotation inversion axis. What we use is the symbol n bar or minus n. So once again, it could be a 2 bar, a 3 bar, a 4 bar, a 6 bar. You can have all of these different rotation inversion axes. Now, this is the point where people who have taken group theory before need to watch out. Okay? And I sometimes call this one crystallographers versus the rest of the world. We work with rotation inversion axes. And you may vaguely remember that in group theory people talk about these S-axes, right? That is not a rotation inversion axis. What they do is rotation reflection operations. Okay? So they use a mirror plane. And the group theorists will probably claim that a rotation inversion axis is not a proper symmetry operation. Well, we crystallographers aren't quite as discriminating, otherwise we would claim that a rotation reflection is not really proper. It's a difference in how you describe things. The important thing is crystallographers don't use these SN axes. So don't use them. Yes?
So on that previous slide, if that hand went opposite, would that be a rotational function?
The first application of this, if it was an S4, would have put this hand back here, not in the front. And there will be slides down that shows you exactly how things change, okay? Why is this important? Well, if you use rotation inversion and you look at a simple inversion center, that would be a 1 bar for us, okay? You do full rotation followed by an inversion, or you can leave the rotation out, obviously, right? So that's a 1 bar for us. In group theory, an inversion center is an S2, right? You rotate by 180 and reflect through the plane. So that's different, okay? An inversion center is not a 2 bar. The 2 bar, as a matter of fact, is a mirror plane. Because you rotate by 1/2, you invert, you end up right below the first object. So 2 bar is a mirror plane, while an S2 would be an inversion center, and an S1 would be a mirror plane. So watch it, they are not the same symmetry operations. Why does it confuse people that much? Well, if you think about it with inversion centers and mirror planes, you realize that they are different, okay? The place where people get confused is a 4 bar and an S4 really don't seem to make a difference. Because a crystallographer would look at an object and say, this has an S4, this has a 4 bar axis, while a group theorist would say, oh, this has an S4, and both are right. Why are both right? Well, here are our 2 operations. We start with a central atom. There's 1 atom sticking off it, okay? If we apply a 4 bar once, so Nathan, now we are getting to exactly what you were asking about. We rotate by 90 degrees, and remember to always rotate counterclockwise. So we rotate by 90 degrees, and then we invert through the center of this ball. That means we end up here, okay, sticking out. If we apply an S4 once, we end up back here, we reflect through, we end up with a ball that is pointing into the board, not out of the board. Okay? So the first object that is generated is different. However, of course, you don't just apply it once, right? Any kind of 4-fold rotation is applied 4 times. Well, if you apply it here again, you go over here, you reflect through, you end up with an object here. Then you go around another 90 degrees, you reflect through, and you get that object that is pointing back here. And then the last time you go back to your original one. So what you end up with is a set of 4 balls around the central ball, regardless of whether you apply a 4 bar 4 times or an S4 4 times. Down here, you create this one first, that one second, and that one third. Up here, you create this one first, that one second, and that one third. So the order in which you create them is different. But that is why people often get confused, because the end result looks the same. Okay? For a 4 bar and an S4, that's true. For some of the other ones, it's not true. Like we just said with the 1 bar and the 2 bar. They are different operations than S1 and S2. And that's why you need to make sure that in crystallography you use your 1 bar, 2 bar, 3 bar, 4 bar, 6 bar. Okay? Inversion is a reflection through a point. Okay? So a mirror plane would mean anything goes straight through the plane at a 90 degree angle to the plane. An inversion center is this one point, and it's like a lens. Everything focuses to that one point and then gets spread out again. So something that is over here doesn't go down here, it goes through the inversion center and ends up there. That's the big difference. Does that make sense? Now, most of the time, crystallographers use either those abbreviations that we just introduced, or if they actually give you a drawn object, they don't like to label things there and say, oh, there's a 2 here with an arrow pointing somewhere. We usually use graphical symbols. Okay? And this is a kind of a sneak peek at how we usually do things. We use little polygons to indicate rotation axes. Twofold rotation must have 2 corners. Okay? Given that we can't really draw a line, that would be confusing. We kind of make it a rice-shaped entity. The 3-fold axis is a triangle. 4-fold axis is a little square. Can you guess what a 6-fold axis would be? Little hexagon. Exactly. Why do we like to use this? Well, for example, this cube has a lot of rotations. If you had to label all of these with little numbers and figuring out which way they point, would probably be a bit tough. Okay? So we like using these simple graphical representations. We just draw a square here in the face center. And we have a little line sticking out that indicates the direction of the rotation axis. Okay? That way we can indicate all the different rotation axes of a cube without being too confusing. And we will be using these a lot, okay? So, it's in your best interest to get used to them. Because you will meet them, you will need to be able to interpret them. You will also be asked to use them to fill in certain diagrams. We'll talk about those more in this handout, because that is what you will find in most crystallographic books, papers, things like that. For that matter, in these handouts, okay? Or in your homeworks. They will show up everywhere. So, the basic symmetry leads us on in crystallography to what we call point and space groups. This is really what a lot of crystallography is built upon, so we will need to spend some time on this to make sure everybody understands it. Where it comes from is, we just talked about individual symmetry operations, but many times in a crystal you'll have more than one symmetry operation. Okay? For that matter, anybody who has ever dealt with symmetry knows that often you can find more than one symmetry element in an object, right? Same holds true in crystals, most certainly. But, once again, you cannot just throw any odd number of symmetry elements together. It's not that just because you choose that this and that should be in the same object and nothing else, that can actually hold true. What are examples for that? Well, if you take your brick, okay, you have 2 perpendicular 2-fold axes, right? Can you just choose that you have 2 perpendicular 2-fold axes and not the third one? If you choose that, you're choosing to live in a world of illusion, okay? It's not possible. If there is 2-fold symmetry here and there is 2-fold symmetry here, we are all of a sudden constrained to having a system with all 90-degree angles, because otherwise we couldn't have that. You cannot have 2 perpendicular 2-fold axes, because a 2-fold, oh yeah, it's a 180-degree rotation, right? So you cannot have that without having all 90-degree angles. Well, if you have all 90-degree angles, you immediately have that last third 2-fold axis, okay? So, something that only has 2 perpendicular 2-fold axes will not exist. That's just one example. There are many more things that can or cannot go together, okay? In addition, our crystal has to reproduce itself in 3 dimensions, right? You don't have crystals that have a hole pattern in them. We don't do those. So, that actually means, that explains why in that last handout there were only 2, 3, 4, and 6-fold axes listed. You may have been wondering why that was, right? Well, The reason for that is only 2, 3, 4, and 6-fold rotations will produce space-filling patterns. And if you are required to fill all space by the unit cells, then you are constrained to these rotation axes. Okay? The allowed symmetry element combinations that exist are called point groups. The allowed point symmetry operations that can be combined. As a matter of fact, there are 32 three-dimensional point groups. I would like you to remember that number. Okay? 7 crystal systems, 14 Bravais lattices, 32 point groups. That already shows you that there once again seem to be some limitations, because we had quite a few different symmetry elements. We have 14 Bravais lattices, or at least 7 crystal systems, and we only end up with 32 point groups. Right? This slide shows you why you can only have 2, 3, 4, and 6-fold symmetry. Okay? 2-fold? Does that fill over space? Sure. 3-fold? 4, 6. If you go to 5, 8, 7, any other number, you will always end up with some areas that you cannot fill by a repeat pattern. It's not possible, okay? So that's why those are not allowed rotation axes in crystallography. So on to these point groups. All of these point groups allow you to have a three-dimensional repeat pattern. That is the most important thing in crystallography. They contain a bunch of combinations of symmetry elements, and as we said, we have 32 of them. And here's a table that can come in very handy. It lists all of these point groups. And one of the things that is immediately obvious is it kind of splits them up by crystal system, right? And none of these are listed for several crystal systems. So as you can see, the crystal lattice symmetry already dictates what kind of symmetry elements you can have. Well, it kind of makes sense, right? If anybody remembers what that triclinic cell looked like, can we have any kind of rotations in that one? There are no 90-degree angles, right? So we cannot have any rotations. So what are the only point groups? 1 and 1 bar. You can have no symmetry or an inversion center. This is where it is important to realize that 1 bar is the inversion center, okay? Because crystallographers use it here. It doesn't say I, it says 1 bar. So, that's triclinic. And that already finishes triclinic. Pretty boring system, huh? When it comes to symmetry, very boring. Also means you have to describe a lot of the atoms in the unit cell if you ever end up with a triclinic crystal, okay? Symmetry doesn't help you a lot there. Next crystal system would be monoclinic. Monoclinic has two 90-degree angles, right? So we can have some 2-fold rotations. They are compatible with 90-degree angles. We can have mirror planes. And it lists 3 point groups for you. 2, M, and 2 over M. Now, the 2 is what? 2-fold axis. So there's your axis. And we rotate by 180 degree. Okay? What would M mean? Mirror. So we have a mirror plane through which we reflect. And then we have that third thing there, which looks like 2 divided by M to most people. We usually call it 2 upon M or 2 over N. What does it mean? It has something to do with rotating and reflecting, but it's not one symbol, okay? It's actually two symbols. What this means is you have a twofold and you have a mirror plane perpendicular to the twofold, okay? So this slash in crystallography implies that the symmetry element listed after it is perpendicular to the first one. Make sense? Now, why do we do it that way? Well, this goes to this back part of this table, okay? You see something there about symbol meaning and appropriate to position. And we will be going back to this table, okay? You will not be able to grasp all of this the first time. Nobody expects you to. This is rather complex, but you'll see that it's useful as we keep going. Monoclinic. Does anybody remember what a monoclinic cell looks like? Any relationship between A, B, and C? Shu says no. They can all be different. All axes are different. How about the angles? Beta is not 90 degree. Alpha and gamma are 90 degree, right? So, if alpha is 90 degree, alpha is the angle between what axes? B and C. Gamma is the angle between what? A and B. So B forms a 90 degree angle to both of the other axes, is what that says, right? So your twofold rotation has to be along B. Because otherwise one corner of the unit cell wouldn't end up on another corner of the unit cell, okay? All of your symmetry elements have to image the unit cell onto itself. Otherwise something is wrong. So, the twofold has to be along B. How about the mirror plane? Has to, in all cases, be perpendicular to the B axis, right? At a 90 degree angle to it. This M, with nothing else written, actually implies that that mirror plane is perpendicular to whatever position it stands for, okay? Because otherwise I need to define two directions to describe a plane, right? The easiest way to describe a plane is to describe what it is perpendicular to, because that means only one direction needs to be defined, and my plane is perfectly defined, right? This, as a perpendicular, defines the plane of this table. Otherwise, I have to give you two vectors. And it tells you that all of the symbols are along Y, so that's the B axis, right? So either a twofold along the B axis, the mirror plane perpendicular to the B axis, or you could have both at once. Well, how do you list two things as both being for the same position? You need to make sure that people recognize that it is one symbol, okay? And that's when we use the slash. So 2 upon M means both of these are with respect to the same symmetry direction in that crystal. If I wrote 2M, I would imply that this is dealing with two different directions. But in monoclinic, we only have one direction along which we can have symmetry. So that would really start screwing things up. As you can see, in other systems we may have several directions. Orthorhombic, X, Y, and Z, all of them can have symmetry, right? It's a brick. all 90-degree angles. So as you can see, you can have symmetry along X, along Y, along Z. Once again, what kind of symmetry can you have? Two-fold or mirrors. And again, the assumption is the mirror is perpendicular to the direction for which the symbol stands. In this case, you write down 3 things for your point group. And given that there's no real preference with regard to A, B, C in the orthorhombic one, right? There's no special axis in orthorhombic. We just go by alphabet. X, Y, and Z. So if you had only 2 folds, you would call it 2, 2, 2. If you had mirrors perpendicular in each direction, you would call it M, M, M. If you have a mixture where you have mirrors in 2 directions, but not in the third, you call it MM2. Could you call it 2MM? Theoretically, sure. It's a brick. You can rotate that brick however you want. By convention, people usually call it MM2. That would be one of those where I would probably not be very picky on an exam, okay? If you realize that the symmetry is MM2 and you write 2MM, unless I defined the axis systems, so you should know that it is actually the Z direction in which there's only twofold. No big deal, 2MM and MM2 are the same thing. Tetragonal starts to get interesting, because tetragonal has one unique axis, right? The C axis is different than the A and B axes. And that means that we can have different rotational symmetry. As a matter of fact, any tetragonal system will have 4-fold rotational symmetry along the C axis. Has to, right? Because A and B are equal. While in the other directions, it looks pretty much like orthorhombic, so you can only have 2-fold symmetry. In this case, the first entry into your symbol will be standing for along the Z-axis, because that's the unique axis by definition. Okay? So we don't go by alphabet anymore. We put the special axis first. So the first entry will be a 4 or a 4 bar. And then once again, in the other 2 directions, you can have 2 or 2 bar. Now this one already gets a lot more complex. Up here, we had only one entry. Here we had X, Y, and Z. Here, our second position in this symbol, all of a sudden, stands for 2 directions. Okay? The 4 faces on a tetragonal cell are identical. If you have something through one of those faces, you also have the same symmetry through the other one. Otherwise your 4-fold symmetry wouldn't hold. So anything along X will also exist along Y. So you don't give it 2 entries for that, because you would be repeating yourself. So whatever stands in the second position stands for any kind of symmetry element that you find along X and Y. The third entry in this one, 45 degrees to X and Y. Okay, so that's kind of the diagonal going through the edges of your tetragonal cell. So that's something to watch out for. What would 4 imply? Well, 4 implies, first of all, that crystallographers are lazy. We are not spelling out that we didn't see symmetry in the second and third position. Okay? That's something that you need to get used to. If there is no way to confuse it, if you know crystallography, crystallographers don't spell it out. That can make it tricky for the beginner. Okay? Because once you know the rules, there is no way to confuse it. for you who are just getting used to all of these symbols, there is plenty of space to confuse things, okay? 4. You need to get used to recognizing 4 means tetragonal. Okay? That's one of those things that you need to absorb as quickly as possible. That means this symbol always indicates tetragonal already, whether there is something following it or not. 4, 2, 2. That would mean we have a 4-fold along Z, a 2-fold along the X and Y, and 2 folds along the diagonals. Notice, it will have either 1 or 3 entries. There are no tetragonal cells with only 2 entries. Doesn't work. Okay? Once again, it's one of those, if you have certain symmetry elements, they draw others after them. Trigonal. That is a different setting for rhombohedral. Any rhombohedral cell can be transformed to a cell that on first glance looks kind of hexagonal. Okay? It would have A and B as equal axes, C different, and it would have one angle that is 120 degrees. So you can transform a rhombohedral cell to what some people call a hexagonal or trigonal setting. It should really not be called hexagonal. The lattice constants may imply that. But the highest symmetry in this kind of system is going to be 3-fold. Okay, that's why we call it trigonal. Stands for 3. First entry of anything trigonal. 303 bar. Starting to see some kind of trends here? Hexagonal. First entry in each of these symbols is a 6. All hexagonal cells have 6-fold symmetry. That's the big difference between these two. Even if the lattice constants may look very similar. Does it have 3-fold or does it have 6-fold symmetry? So these are pretty easy to recognize once you realize what you're looking for. Okay? And all of them, the first entry corresponds to the C-axis, because that's the special axis in all of them. Cubic is the one that gets a bit more confusing. Okay? Could have 2 entries, could have 3 entries, could start with an M, could start with a 2, could start with a 4. Gee, what a mess. Isn't it? The way I recognize a cubic cell when it comes to these little point group things, what do all of them contain, all of these symbols? A 3, right? But where does the 3 stand? Second symbol. If it is a first, it's trigonal. If it is a second symbol, it's a cubic cell. Now, what does that correspond to in a cubic cell? As we said, there could be more than one direction that is described by one of these entries. The first entry in a cubic cell describes A, B, and C, right? Because the 3 directions have to be identical. Remember? So, the second entry is not going along any of the unit cell axes. The second entry would probably confuse you if you just looked at this table, okay? At 54.74 degree to XYZ. Oops, what the heck is that? What it is, and what is much easier to remember, it's the body diagonal. Okay? The body diagonal of the cube from one corner all the way across. If you look down the body diagonal of a cube, what symmetry do you see? 3-fold, right? So that is where that 3 comes from. That's the body diagonal of the cube. So any symbol that has a 3 on the second position has to be cubic. As I said, we'll revisit that table. But that is your first brief overview of how knowing something about the crystal systems combined with symmetry elements really gives you a lot of power, okay? I can look at a little combination of these numbers and m's, and I can tell you what does the unit cell shape look like. If you think about that, that's very powerful, isn't it? What you once again find in some of these is the 6 upon m, or 4 upon m, okay? That means it's the first symbol. So in this case, for example, it would be a 4-fold rotation along C and a perpendicular mirror plane. It always means the perpendicular. Now, those were the point groups, 32 of them. What you have in crystallography is space groups. That is what people usually report when they report on a crystal structure. What does a space group contain? First of all, lattice symmetry. We already talked about that one. Okay. It contains all of these point symmetry elements, which are not translational, right? No translational component. And it also contains some additional symmetry elements that you don't learn about in group theory, because they once again have a translational component. They are glides and screw axes. And all of the combinations of symmetry elements that you can have give you 230 space groups. That is the basis of crystallography, 230 space groups. Now, I do expect you to know these numbers here. 7 crystal systems, 14 Bravais lattices, 32 point groups, 230 space groups. I will obviously not expect you to memorize 230 space groups. Okay? For that matter, I haven't memorized them. There's a big blue book, it's about this thick, that big, has all of them in it, and all the information that you may or may not want to know about them. That is what you open if you have to deal with these 230 space groups. So, what are those additional symmetry elements that most of you have probably never heard about? Screw axes. Well, everybody knows what a cork drawer looks like, right? I think it's kind of an example of what screw axes are. They are certainly axes, rotation axes, but they also kind of translate things as you go, okay? The way we designate them is n sub n, okay? So we have 2 numbers here, little subscript. This is an example of a 2-1 screw axis, as we would call it. What does a 2-1 screw do? It rotates by 180 degrees and it translates by 1/2 along the unit cell in the direction in which the screw axis is pointing. So, it's rotation and translation, right? And whether you first rotate and then translate, or first translate and then rotate, you end up with the same result, okay? How does this look? Well, here would be a molecule, and so basically, if this is sitting on one unit cell edge, then this would be sitting on the next unit cell edge. But you also generate this one down here. How do you generate it? Well, you move half of the unit cell over, and you rotate by 180 degrees to go here, okay? So this would be this 2-1 screw axis. Well, if you draw kind of the path between all of these molecules, it kind of looks like a screw. Do we only have 2-1 screw axes? No, absolutely not. We have all kinds of screw axes. Here are some examples. The way we designate them is we always use 2 numbers. Okay? 1 gives you the order of the screw, the big number. 2-fold, 3-fold, 6-fold. But then you have this little subscript n, and that one is very important, because that one tells you how far you translate. Okay? And by definition, you take this little number n and you divide it by the order of the screw to figure out how far you translate. So in the example of the 2-1 screw axis, you would have 1 divided by 2, that's 1/2. So the translation of a 2-1 screw axis is 1/2. Okay? Here's a 3-1 screw. The translation of this one would be 1 divided by 3, 1/3. Does that make sense? Let's look at it. Here's your first object. You rotate by 120 degrees, you translate up 1/3. You take this one, you rotate by 120 degrees, you translate up another third. And you rotate again, 120 degree, you translate up the last third of the unit cell, and you're back to your initial object. Okay, so here's your 1 unit cell. So it's a 3-1 screw. As I said, we can use different numbers. How about a 3-2 screw? It's the second example, okay, a 3-2 screw. By definition, how far do we translate? 2/3, right? So let's check. Here's our first object. We rotate 120 degree and we translate up. Well, that does look like 2/3, right? So then we need to use this object. We rotate by 120 degrees. We translate up another 2/3 of a unit cell. We haven't made it back to our starting point yet, right? So we rotate 120 degrees. We translate up 2/3. We end up with an equivalent object, right? Now, this is where you start making use of the fact that the unit cell gives you translational symmetry. If the unit cell is the smallest repeat unit, then anything I find in this unit cell here, do I also need to find it in this unit cell? In the same positions for that matter, right? So, this one here, better also show up in this unit cell. There's no way around it. So I can draw this one also up here. This one I generated in this higher unit cell, well, it better also exist in that one, right? So now I actually need to use 2 unit cells to do my rotation translation to get back to my original object, but I again end up with 3 different objects in each unit cell. And what it looks like if you just went from one object to the next object without looking at the numbers would be this, right? So it would be a different handedness of your screw. Instead of a right-handed screw, it looks like a left-handed screw. What it really is the right-handed one with the 2/3 translation. But what it boils down to once you have all the objects is, it is really the same as having a left-handed screw. How complicated can you get? Well, there's a 6-1 screw. Okay? Gives you this nice little staircase. You can have a 6-5 screw. That would be the same thing, but it looked like it was going the other way around. You could have a 6-2 screw, translating by 1/3. You could have a 6-3 screw, 6-4 screw. You can have any of these, okay? They all exist. And you probably think by now that they are there to haunt you. What about the other symmetry element? And the good news is, this is the last symmetry element type that we will introduce. Aren't you glad about that? There is an end to it. Glide planes. Very common in crystallography. Of course, only if you work with things that can change handedness, because these, once again, contain a reflection. So those of you who want to work with proteins, you may have to worry about screw axes. You probably never have to worry about glide planes. Okay? But you do for this class. So no escaping it. It's a reflection translation. Once again, as I said, all of these have a translational and a non-translational component. You reflect through the glide plane, makes sense, right? And you translate within the glide plane. Now that's kind of vague, right? If I just told you to translate within a plane, would you know where to go? If I tell you translate through this room, how many different options do you have? a lot, right? So there needs to be some rules about what that translational component is, right? And there sure enough are. Once again, this is one of those, there's a very short symbol somewhere, and the crystallographer expects everybody to realize what that symbol means. We have A, B, C, N, and D glide planes. And there are some additional ones that are more complicated, but for the purpose of this class, we will not deal with those. Okay, if you ever encounter them, you will know enough crystallography to talk to a crystallographer and figure out what double glides are. This is plenty of food for your brain to deal with in this class. So we'll restrict ourselves to the A, B, C, N, and D glide planes. What are they? Well, an A, B, or C glide corresponds to a translation of 1/2 A, or 1/2 B, or 1/2 C. So that's a pretty simple thing, right? If I call it A, I translate 1/2 along A. And reflect through my glide plane, of course. We also call them axial glide planes because we translate parallel to the unit cells, to unit cell edges. So that's probably the simplest glide plane. All of the other ones contain more than one direction of translation. An N-glide is a so-called diagonal glide plane. And it is a translation of either 1/2 A plus 1/2 B, or 1/2 A plus 1/2 C, or 1/2 B plus 1/2 C. And that is where usually the first alarm bells go off in people's heads saying, wait a moment, either or? Is this an N sub A, N sub B, N sub C? How do we know? How the heck do we know whether it is this, that, or that, if all of them just have the symbol N? How can we know? See this little statement here? Translation within the glide plane. Just having a symbol N on a piece of paper with no other relation wouldn't tell you how you translate. But if you know where that N glide is located, and you would probably have some kind of a drawing that shows you, right? Then only two of these axes can be within the glide plane, right? And those are the two axes along which you translate. So you cannot answer which of these it is until you know where the glide plane is in this specific system. Once you know that, however, only two of your unit cell axes can be a part of the glide plane, and as all translation has to happen within the plane, you know exactly which of these three scenarios it will be. Does that make sense? And it's kind of tough to envision these things, I know. But just remember, always translate in the plane. As long as you remember that, you will be able to figure it out. D-glide, not that different from the N-glide. It's called a diamond glide plane. Once again, you have two translational components. In this case, it's not 1/2 and 1/2, but 1/4 and 1/4. And as you can already imagine, it occurs in diamond, or we wouldn't call it a diamond glide plane, right? FD3 by M is the space group of that one. This one, chances are you won't be given too many drawings in this class where you have to figure that one out, because once it goes down to 1/4, you need to measure things, and then the three-dimensional drawing has to be to the point where you can actually measure things without having the problem with, perspective and stuff like that. 1/2, 1/2, I might still expect you to be able to figure that one out because that's much easier, okay? I do want you to know the definition of a D-glide, but I probably won't ask you to find one in a drawing. They aren't that easy to spot. So what does a glide look like? Here's an example of a glide. Once again, here's a molecule, Here's the next molecule in the adjacent unit cell. There's another molecule down here. If you translate by 1/2 A and you reflect through this plane, you get this molecule to go here. Okay? This would end up right there, right between. And then you go through the plane, you end up right there. This atom here would be translated to about here. You go through the plane, you end up right there. And then of course you could take this one, you translate by another 1/2, right between these two, you reflect up, you end up back here. So there's your A glide. And these are the ones that will require some training of your eyes, okay? Most of us are used to spotting mirrors or spotting rotations. Glides are something we haven't dealt with a lot until we encounter crystallography. We'll be doing exercises, don't worry. You will learn to spot glide planes. So, as I said, crystallographers like using symbols, because if you actually have a crystal or a drawing, any kind of symmetry drawing, using graphical symbols is much simpler than trying to indicate and draw and put in words where what symmetry element is. You will be held responsible for knowing these symbols. And that seems to be a lot right now, but we will be using them, so you will get more familiar with them. But do make sure that you know these symbols. You will need them. We already talked about some of these. 2-fold rotation, 3-fold rotation, 4-fold. There's your 6-fold, the hexagon that you guessed, right? In addition, you have screw axes. How do we indicate a screw axis? Well, we put little things sticking out of it that kind of look like a screw. Right? So here's your 2-sub-1. There's your 3-sub-1. Your 4-sub-1. Your 6-sub-1. Note that the sub-1, and on this one you can, they draw it this way, okay, but on the 2-sub-1 it really doesn't matter a lot. On the other ones, notice they are pointing in the direction in which you are rotating, right? You always rotate counterclockwise. So these little things stick out counterclockwise. Remember how we said the 3-sub-2 really looks like a left-handed screw? Look what the 3-sub-2 is drawn like. They are sticking out in the other direction. The 4-sub-3, which is the opposite of the 4-sub-1, right? Look what it looks like. They're sticking out in the opposite direction. Look at the 6-sub-5. So there are actually things that help you remember these once you realize what they are. And then of course we have these screws where it is not a sub-1. The 4-sub-2 only has 2 of these things sticking out. Okay? Because we translate by 1/2, so we generate only 2 objects. Yes?
So the little things point in the direction of the rotation?
That is how I like to remember it, okay? These little things point in the direction of the rotation. Now we would still rotate this way, even on this one, and translate 2/3, but as we said on that drawing, it looks like we are rotating the other way and translating 1/3. Okay? So this is just a little memory helper, as you could call it. Same way here. We reduce the number of little things sticking out if we have a 6-sub-2, 6-sub-3, or 6-sub-4 axis. The 6-sub-2 translates by 1/3. Very good. That means we translate 1/3, 2/3, and a full unit cell, so we create 3 objects. How many are sticking out? 3. Okay? So there are reasons for why people chose these symbols. They look extremely confusing the first time you see this page, and you're like, oh my god, what is this? But once you realize what they stand for, they do get a lot more friendly.
So the 6 sub 4 is
It's the mirror image of the 6 sub 2. Okay, so once again, it would be a 2/3 translation, but that again looks like a left-handed 1/3 translation once you generate all the objects. Similar to the 3 sub 2.
So for this 2/3, how many dimensions?
Well, 2/3, 4/3, 2, right? That is when we are back to a full number. And remember, whatever we generate in this unit cell also has to be in the other unit cell. So once we generate the equivalent ones, we again have 3 objects in one unit cell. There are your 3 little handles sticking out. Okay? That is where that one comes from. Now, if you thought this was all the symbols we had, bad news. There's more of them. There's an inversion center. It's just a little empty circle. That's easy, right? Then we have 3 bars, 4 bars, 6 bars. We have combinations where we have an inversion center on top of some kind of either rotation or screw axis. In that case, we just leave the little open circle, okay, in the center of our screw axis or our rotation axis. We have a mirror plane, which we just indicate with one nice thick line. That's easy to draw. Our glide plane, we just do kind of a dashed line. For the most part, you'll find that one or this one. This depends on whether you're usually in 1 or 2 dimensions, okay? As I said, don't worry about the double glides. We won't be dealing with those. Diagonal glides would be dash dot, dash dot, dash dot, just so you know if you see them on a diagram what they are. So there are some of these symbols. I expect you to know how to indicate mirrors or axial glides, okay? The other ones, you know where to look them up if you ever need them. And of course, I expect you to know your rotation axes. You will need those. So, this gets us to, obviously space groups contain all of these. And what you will be given in a paper is a very short space group symbol. And crystallographers kind of expect people to be able to interpret this very short symbol and figure out something about this crystal. As I said, crystallographers are lazy or efficient, depends on your point of view, but it can be confusing to the beginner. What are the rules? First of all of our space groups start with a letter, and that is a capital letter for space groups. Okay? It could be an F, it could be a P, it could be an I, it could be an A, a B, or a C. That's it. If you think back to the Bravais lattices, you should have some idea of what they stand for. Primitive, body-centered, face-centered, or one of the base centers, right? So, the first entry in the space group symbol tells you something about lattice centering. That could already limit what kind of crystal symmetry you can have, right? Because not every crystal system can have all kinds of centering. If it is not primitive, it won't be triclinic. You immediately know that. And then it is followed by a collection of symbols that indicate the symmetry operations in the different lattice directions. And a real hardcore crystallographer can derive the entire drawing of all the symmetry elements from the space group symbol. In a simple case, I might expect you to be able to figure it out with enough time. In a complicated case, I would say, open that big blue book. It'll give you the answer. Okay? So I'm not going to expect you to take like FD 3 bar M or something like that and give me the space group drawing. Okay? I will not do that to you. I promise. Now, there are shorthand notations for a lot of space group symbols. Most crystallographers would have no hesitation to write P2. What it really should be if you spell it out is P121. Now, if I look at that, I can immediately tell you it's a monoclinic space group. Why can I tell you? Because I know that in monoclinic cells you only have one symmetry direction along which you can have symmetry elements, right? Remember that table? So if there's only one entry and the highest rotation is twofold, I know it's monoclinic. This would probably tell it more to you. P, no symmetry along A, twofold along B, no symmetry along C. Okay? With a little bit of time and thinking and looking at the crystal systems, you could probably figure out from that one that it is monoclinic. The crystallographer may only give you that one. Because they say, there's only twofold symmetry and only one entry, it has to be monoclinic. And you will get to learn that, to recognize that, okay? Other symbols cannot be abbreviated. P212121, one of the most favorite space groups of proteins. You cannot abbreviate that. You can't leave out one of those two ones. It's orthorhombic. You need to specify your entries along X, Y, and Z. You cannot leave them out. Okay? Because there is symmetry along each of these directions. Now, does that hold true for all orthorhombic cells? No. And that is where life can get confusing. CMMA. The full symbol would be C, 2 upon M, 2 upon M, 2 upon A. The crystallographer leaves out all of these twofolds. Because the crystallographer knows if I have reflection operations perpendicular to all three axes, I also have to have my twofold axes. Crystallographer knows that. So crystallographer often just writes that. So these are so-called implied symmetry elements. Because you have certain elements, there have to be other symmetry elements. And it will take you a while to get used to that and to really get a feel for this. But that is something to always keep in mind. Now, that was in 3 dimensions. Okay? There are some limitations. You can combine certain things, you cannot combine other things. Or sometimes you are forced to combine things, like that CMMA. It must have the twofolds. What this gives you, we already addressed that, is for 3 dimensions, 14 Bravais lattices, 32 point groups, 230 space groups. Okay? Now, we will also be spending some time working in 2 dimensions, because it's just easier at the beginning. In 2-dimensional lattices, we have 5 different lattice symmetries. We have 10 point groups and 17 plane groups. What are those plane groups? Well, the next 2 slides show you all of these plane groups. What they give you, here's a unit cell, okay? And there is some object. This could be a molecule, could be anything, sitting right inside the corner of the unit cell, and it shows you where else does that object show up. Well, in this case, in P1, and notice that for plane groups we use a small letter, not a capital letter. 2 dimensions gets the small letter. 3 dimensions gets the capital letter. Don't mix them up. You change dimensions if you use the wrong letter. So in P1, no symmetry. So all you get is elements in the corners of the unit cells. Here is your unit cell with the indicated symmetry elements, and it looks very boring indeed, because there are no symmetry elements. Right? Next one, P2. Well, it generates more of these. Obviously, each of these also has one over here, right? And that is because there's a twofold at the corner of the unit cell. That makes this one go here. Twofolds at the corners also generate twofolds in between. There's no way around that. Because once you have drawn these things, you see that there's a twofold axis right here. They are generated by the initial symmetry elements. Here's a mirror plane. As I said, we use a solid line for that. Okay? That just generates these two objects, and once again you get an additional mirror plane. Here's a glide plane, which in 2 dimensions we just call G for glide. Okay? Because in 2 dimensions, obviously we need to translate along that G and then reflect through it. Dotted line. As you can see, it gets a bit more complex. Then you can combine things. P2MM, P2MG. Notice that anything with a mirror has 90-degree angles. P2GG. In these cases, all of the rotation axes go into the plane of the paper, obviously, right, because it's a 2-dimensional object. So that's the first entry, and then the M's and G's would correspond to the 2 directions in your 2 dimensions, your 2 axes. Okay? Can it get more complicated? Sure. There's the rest of your 17 plane groups. Here's a centered one. As you can see, the object that was here also shows up in the center. Okay? There's another centered one with higher symmetry. Here are the ones with 4-fold symmetry, 3-fold, 6-fold. A lot of symmetry elements. We will be practicing that in the very near future. Okay? So what you need to make sure is that you know what these symbols are. What are those symmetry elements? That is your number 1 task. Now we are almost through this handout, so let's briefly finish it. Back to the 3 dimensions. In 2 dimensions, we have a limited number of symmetry elements, right? All rotation axes are perpendicular to the plane of the paper, and then we have the line and the dotted line for mirrors and glides. In 3 dimensions, you could have symmetry elements parallel to the plane of projection. And they will be indicated in those drawings, and you should be able to recognize some of them. A mirror plane parallel to the plane of projection is indicated with this little symbol. Okay? Just a little corner. The glide plane would get an arrow because you also translate. Don't worry about these. If you ever meet them, you know where to look them up. These you may have to use. These you certainly need to recognize and be able to use. And these are actually much easier for us to remember. For a 2-fold rotation, we draw a little arrow. Okay? So, if you have an arrow drawn like this, it means there's a 2-fold rotation in the plane of this paper. 3-fold rotation, you can't use an arrow, right? So you actually draw the symbol. Where's our 3-fold? They didn't draw it on here. Well, so we'll use the 4-fold. There's your 4-fold. You draw that symbol on a stick. Okay? So it shows me that this is the direction of the axis, but it's a 4-fold. So it's parallel to the plane of this paper. And there will be times when you will meet them or need to use them. So make sure you have some idea of what these are. You can do that with any of these. Okay? Any of the rotation axes. Those are the ones that you should have some idea of. There are more. Okay? This slide is just there for your amusement. Do not memorize these. These are symmetry elements that are inclined to the plane of the projection. Know that they exist, so if you ever meet one of those symbols somewhere, you know where to look for its explanation. You realize this is actually a symmetry element, I can figure out what it is. Okay? I will not expect you to memorize these or to draw these or to recognize these. But for completeness, I decided to put them onto this slide. All right, and I think that is it with this handout. Was a lot of stuff today, okay? Next class, we will be doing a lot of practicing, because we need to learn to use those symbols. Make sure that you know how to draw your rotation axes, your mirror planes, and your glide planes, how to indicate the symbols, because you will be needing them in the next class. Any questions at this point in time? All right, they might come up as we go. Those of you who arrived a little bit late, the first homework set was handed out.